Hi students, in this video class I will be discussing about electrostatics of conductors. That means some important properties of conductors related to electric field, potential and charge. We know very well the difference between insulator and conductor. Insulator doesn't have any free electrons, whereas a conductor have free electrons, right? So electrostatics of conductors. The first point in this is electric field inside any conductor is zero in static condition. Static condition. That means what? You have some conductor, right? Let's say this is a neutral conductor. Neutral mode, right? Net charge is zero, but it can have free electrons. Inside this, electric field is zero. Or you might have a positively charged conductor, even then electric field inside it is zero. Or you might have a negatively charged conductor. Inside this negatively charged conductor, electric field is zero, right? So whether it is a neutral conductor or a charged conductor, electric field is zero. Or you might have a conductor in the presence of external electric field. In the presence of electric field, then also inside the conductor electric field is zero. We already know charge always resides on the surface. All the charges will be distributed in such a way that electric field inside it is zero, right? So what do you need to remember? Electric field inside any conductor is zero in static condition. Static condition means what? You know, all the charges might move and distributed in such a way that there is no further motion of charges. Then electric field inside the conductor is zero, and this is one of the important points, right? And the second point, at the surface of a conductor, at the surface of a conductor, right? At the surface of a conductor, electric field is always normal to the surface. Always normal to the surface. Or I can say must be normal to the surface. Means what? For example, you are having a conductor. You are having a conductor, right? Let's say it is negatively charged conductor. Negatively charged conductor, right? Now, or let's say it is positively charged conductor. Positively charged conductor. Let's say if the electric field is not normal, then what might happen? That it is not normal. Some angle it is making with the surface. Let's say this one is making an angle theta with the surface. Electric field is a vector. It can be resolved into how many components? Two components. One component is E cos theta and other component is E sin theta. So, there is one component which is parallel to the surface, right? But on the surface, what are present? Charges are present. So, there is a force acting on those charges. So, what is the force acting on those charges? Q into E cos theta. But in static condition, that means all the charges are at rest. When all the charges are at rest, net force must be 0. So F is equal to 0. F is equal to 0, right side, QE cos theta is also equal to 0. That means cos theta is equal to 0. So theta is equal to how many degrees? 90. Right? So under static condition, these charges that doesn't move. So net force is 0. QE cos theta 0. Cos theta 0. Theta is equal to 90. Theta is equal to 90 degrees. That means what is the meaning of that? So the electric field must be normal to the surface. From this we can conclude that electric field must be normal to the surface. Will you agree with that? Electric field must be normal to the surface of the conductor. So even if it is negatively charged conductor also, then also electric field must be normal. If it is negatively charged body, electric field will be perpendicular to the surface, that is towards the surface. Is that clear? Will you agree with that? So what point you should remember? At the surface of a conductor, electric field is always normal to the surface. Right? This is the second point. And then the interior of a conductor, can have no excess charge. The interior of a conductor can have no excess charge. What is that? Inside any conductor, there will not be any charge at all. That means, if I take a conductor, I need to prove that charge inside the conductor must be 0. So, what I do? I take a Gaussian surface. If I take a Gaussian surface, closed integral E bar dot ds bar is equal to charge enclosed divided by epsilon naught. But this is a conductor. We just saw that electric field inside any conductor is 0. So electric field is 0. That means, so charge enclosed divided by epsilon naught is equal to 0. So charge enclosed will be equal to how much now? 0. That means inside this, any charge will be there, no charge will be there, no charge will be there. You can take any small volume or you can take every 0. That means, finally, what is our conclusion? Inside any conductor, charge will be 0. What is the meaning of that? Charge always resides on the surface. Charge always resides on the surface of the conductor. Please remember. So I can also say now, so charge always resides on the surface of the conductor. Charge always resides on the surface of the conductor. Right? Is that clear? I hope you have understood. Next point. Next point. Potential at each and every point on the surface and inside the surface has same value. Potential at each and every point on the surface and inside the surface has same value. What is the meaning of that? That means you take any point inside the conductor, potential is V in. You can take any point on the conductor, potential is V on. According to this, potential inside is equal to potential on. So that means potential throughout the volume of the conductor is same. So that means what's the meaning of that? Potential throughout the volume of the conductor. So throughout the volume of the conductor is same and has same value inside and on the surface. Of course, okay, that statement is meaningless. Then how to do this? Right? So for example, you take 2 points. Point 1 here, point 2 here, point 3 here. Right? In static condition, we know that, we know one relation, E is equal to potential difference by D. So E is equal to potential difference divided by D. We know this relation. So what I did here? Here 1, potential at this point is V1, potential at this point is V3. So potential difference is V1 minus V3 divided by some distance. So don't worry about distance. Now, in static condition, electric field is 0. That means V1 must be equal to V3. Let's say you take point 2 here. So E is equal to V by D. In static condition, electric field between these 2 points is 0. If electric field is 0, that means V1 minus V2 divided by D is also 0. That means V1 must be equal to what? V2. So from this I can conclude that V1 is equal to V2 is equal to V3. So what is the meaning of this? So throughout the volume of the conductor, at each and every point inside the conductor or maybe on the surface of the conductor, potential will be same, and that is 4th point. Have you understood? Right. field is 0. Actually, electric field will not be 0. E cos theta is equal to V by D. Why E cos theta we have to take here? Andre parallel component. Okay, parallel component. Because if there are charges on the surface, so the electric field component parallel to the surface is E cos theta. And this E cos theta will be 0 actually. If E cos theta will be 0, that means V1 will be equal to V3. But let's say inside this we have E is equal to V by D formula. Inside this E is equal to V1 minus V2 by D. But electric field inside the conductor is 0. That means V1 is equal to V2. That means throughout the volume at each and every point on the surface of the conductor, at each and every point inside the conductor, potential is 0. Right? Sorry. Potential is same, not 0. So at each and every point on the surface of the conductor, at each and every point inside the conductor, potential is same. Right. Next point. Electric field on the surface of any conductor is E bar is equal to sigma by epsilon naught into n cap. That means if I talk about magnitude of electric field, so magnitude of electric field is equal to magnitude of sigma divided by epsilon. You can take any conductor. So on the conductor, that means on the surface of the conductor, what is the electric field? Sigma by epsilon. How? So for example, you are having a conductor like this. Right? Imagine a small area on the surface. You imagine a cylinder like this. Imagine a cylinder, right? Let's say this one is positively charged. So this one is positively charged. We know well, electric field is always away from the positively charged surface. And here, this side there is no electric field. Why? Electric field inside the conductor is 0. So this side here there is no electric field. So now if I take the surface like this, we are having electric field E bar, and I can have area vector ds bar. You know, starting in Gauss law, we have seen that area vector is always perpendicular to the surface. It should be outward normal. So this ds bar is the area vector which is perpendicular to the surface. Then, is that here? Now, if I take this entire cylinder, so closed integral E bar by ds bar is equal to, let's say, charge on that small area is dq divided by epsilon. Of course, here there is no electric field. Here only there is electric field. So E bar and ds bar. So both of them are parallel. That means here what I get, EDS is equal to dq divided by epsilon. So I am taking a closed integral. Means what? I am taking a closed cylinder. I am taking a flux through this cylinder. Of course, here there is no flux. Here only there is a flux. So EDS. So E is equal to dq divided by ds into 1 by epsilon naught. So E is equal to dq divided by ds. So dq divided by ds, what is that? Charge per unit area. Charge per unit area, what is that? Surface charge density. So sigma divided by epsilon naught. So what's the final conclusion? Electric field on the surface of any conductor is sigma by epsilon naught. Positively charged body means electric field will be away. Negatively charged body means electric field will be towards. That's why the unit vector. That's why we are having unit vector. The unit vector represents only direction. Positive charge means away. Negative charge means towards. I hope you have understood this, right? Then electric field inside any cavity is zero. Electric field inside any cavity is zero. Electric field inside any cavity is zero. What's the meaning? For example, you have electric field inside any cavity is zero in a conductor. Right? So, for example, you have a conductor. There is a cavity. There is a cavity. Some hole is there. Now, electric field inside this cavity is zero. How? Right? If I take a Gaussian surface, then if I use Gauss law, closed integral E bar ds bar is equal to charge enclosed divided by epsilon naught. So E ds integration closed integral E bar ds bar. But we already know charge inside any conductor is zero. Charge always resides on the surface. So what happens inside this Gaussian surface? There will not be any charge. Charge has to exist only on the surface. So zero. That means electric field inside the cavity is equal to how much now? Zero. So we have an iron ball. Inside the iron ball there is a hole. Let's say that if the iron ball is charged, inside that hole electric field will be zero. See, I am telling you here conductors literally means all of them are solid. That means there is material inside the conductor. Right? Is that clear? So, if you are having a solid conductor and if there is a cavity, inside the cavity electric field is zero. Right? Then, for example, there is a conductor. There is a cavity. At the center, inside I am keeping a charge. Inside this I am keeping some charge Q. Okay. Now, this is a conductor now. Now, let us take a closed surface. Let us apply Gauss law. So, closed integral E bar ds bar is equal to Q divided charge enclosed divided by epsilon. But we know inside the conductor electric field is how much? Zero. Electric field is zero. So charge enclosed must be zero. Charge enclosed is zero. But how much of charge is there? There is a charge Q. But this Q cannot be zero. But the charge enclosed must be zero. That means you have another charge inside that. Another charge induced. Another charge induced. Such that net charge must be zero. That means capital Q is equal to what we will get? Minus Q. Means what? For example, if it is a positively charged, so on the surface, what is induced? Negative charge is induced. And what is that negative charge? Minus Q. So, if you are having a minus Q, this side what should be induced? Plus Q. That means electric field inside the conductor must be zero. So, what is the point here? If you are having any charge inside the cavity, the electric field must be inside the conductor must be 0. So there will be an opposite charge induced on the inner surface, and a similar charge will be induced on the outer surface. Is that clear? And this is one important point. So what's the meaning of this? If there is a charge inside the cavity, on the inner surface, opposite charge is induced. On the outer surface, similar charge is induced. But net charge inside this cavity is how much now? 0. And electric field is all. Is that clear? Electric field inside the conductor is 0. Have you understood? Right. Now, electric field inside the cavity is 0 if there is no charge. So if there is no charge, electric field inside the cavity is how much now? 0. This phenomenon or this property is called electrostatic shielding. What do you call that? Electrostatic shielding. So electric field inside any cavity is 0 in a conductor, and this phenomenon is called as electrostatic shielding. Electrostatic shielding. Electrostatic shielding. Right? So, what's the simple meaning of electron? Inside a cavity of any conductor, electric field is 0. This phenomenon is called as electrostatic shielding. There is one very important use of electrostatic shielding. For example, there might be some equipment. The equipment is very sensitive. You want to protect that equipment from external electric fields. Then what you do? You keep that equipment inside this cavity. That's it. For example, there is some equipment. The equipment is very sensitive to electric field. What do? You keep that device or instrument in an iron box. If we keep that inside iron box, now iron box is a conductor. So inside the iron box, electric field will be 0. So the device will not be damaged. Right? For example, you are moving in a car. Let's say. So thunderstorms are falling. Let's say. If a thunderstorm falls on your car, you will not get inside the car. Why? Because you are having car body. So when a thunderstorm is falling on that, huge amount of electric field is present. Now what happens? The interior of the car becomes cavity. So inside the cavity, electric field is how much now? 0. So you will not be affected by that thunderstorm. Is that clear? So if you are having any sensitive equipments, you want to protect them from electric fields, keep them inside a cavity like an iron box so that the device will not be damaged, and this phenomenon is called electrostatic shielding. And one extra point just now I have discussed with you, that is, if there is a cavity, if there is a charge plus Q, on the nearer surface opposite charge is induced, on the farther surface similar charge is induced, and there will be an electric field here. And in this case electric field is not 0. I said, if you are having a conductor, so if there is a cavity, that means if there is a cavity, then electric field is 0. But if you are having a charge at the, if you are having a charge inside the cavity, then electric field will not be 0. Is that clear? Is that clear? But electric field inside the conductor is always 0. Electric field inside the conductor is always 0. Right? I hope we have understood. So let us try to recall the point. Inside a conductor, electric field is 0. So if you are having a conductor, inside the conductor, electric field is 0. And what is the next point? Electric field is always perpendicular to the surface. So, for example, if here there is a positive charge and here there is a negative charge, so electric field lines are always away from positive charge and electric field lines are always towards negative charge. And here electric field is present and here also electric field is present. So there is a surface charge density, there is no surface charge density. There is a surface charge density, right? And then charge inside any conductor is zero. So if you are having a conductor, so charge inside the conductor is zero. Charge resides only on the surface. That means there will be surface charge density. If there is a charge, there is an electric field. Right? And next one. Potential inside, potential on will be same. Potential at any point inside, potential at any point on the surface is same. And electric field on the surface is always equal to sigma by epsilon. So if you are having a conductor, electric field inside the cavity of the conductor is zero. And all these points are very, very important. For PUC exam, they might ask you either for 1 mark questions or 2 mark questions. And for NEET exam, and maybe JEE exam, NEET exam they might ask you theory questions, and for JEE exam they might link with numericals also. They might link with numericals. So when you are solving numerical, you have to use these ideas in JEE exam. For NEET exam, they might ask you 3 questions. For PUC exam, so they are important for 1 marks and 2 marks question.